Thanks, Ryan. Can everyone hear me okay? Cool. Great. Yeah. Exciting to be here again. I'm going to talk about this project Cubed that myself and Tom White have worked on. As Ryan mentioned, I'm currently at Seaworthy, but most of this work that I'm talking about here was done while I was at Columbia, and my position was funded by the Moore Foundation, which allowed us to do this kind of exploratory work. So, second. Okay, so what am I going to talk about? I'm going to give you an overview because there's going to be various parts of this talk. So I want to start off with my personal vision of how science at scale would work in an ideal world. And then after that, I want to describe what Cubed is and the properties of Cubed, how we've integrated Cubed with Xarray, some initial results of using Cubed on a large-scale problem. And at that point, we'll be in a good position to evaluate the pros and the cons of Cubed relative to other alternatives. And after that, we'll talk about future directions and where we want to take this work and how you might be able to get involved or help. So the vision for science at scale, or in other words, my Christmas list. So we're all familiar with the Pangeo stack, the classic image where we have chunked cloud-native storage on the left, fed into compute nodes in the same data center. Some kind of parallel framework executes across many chunks of data, but the users mostly abstracted away from that because they use a high-level framework like Xarray, and then all of this happens remotely, controlled from a small local machine via a web browser web server like Jupyter. This is the picture we normally use, but I'd like to ask the question, if the parallel executor part of this was perfect, then what properties would it have? So this mythical imaginary piece of software, what would it be able to do? So on my Christmas list, the properties I would like, firstly, the parallel framework would need to be expressive. It would need to be expressive enough to express any scientific computation that I wanted to do. I wouldn't want to be hamstrung into only scaling certain types of computations. And in particular, it would be nice if I could scale the computations without rewriting any code at all. Like ideally, I just take my Xarray code, I don't have to change it, and I just run it at a much larger scale with basically no alterations. Dask is actually very good at this because it has lots of high-level abstractions, such as apply ufunc and map blocks, and it haven't really encountered workflows that Dask can't represent somehow. Another property you would like in this mythical perfect parallel framework would be perfect weak horizontal scaling. And what I mean by that is that if I have 1,000 times as large a problem, I want to be able to do it in the same amount of time, given 1,000 times the compute resources. This idea of scaling up rather than taking the same time size problem and doing it in a shorter amount of time is called weak rather than strong scaling. And I feel like this is the type of scaling that's relevant to science because I don't really need to get my work done in a millisecond, but I do want to analyze all the data I have in a reasonable amount of time. I would also like the performance of this mythical framework to be predictable. I don't want at some scale or for some workload where for some obscure reason something goes wrong, perhaps I run out of RAM or in some way saturate something that I don't want to. I don't want that to happen. I want it to behave in a predictable way so that I can reason about how much longer it's going to take or whether or not it's going to even succeed. I would also like to be able to forget about the concept of a cluster because a cluster is not relevant to my science. Really, I just want to say, go compute, and it just happens. And I don't really want to have to think about creating a cluster, looking after the cluster, how big the cluster should be, which I might not really be sure of in advance, especially if I'm not a particularly technical user. And I don't want to have the risk of like forgetting about the cluster and being charged for it staying up when it's not even doing anything. So ideally, in an ideal world, there just wouldn't even be like a cluster to worry about, or it wouldn't be something that as a user I need be concerned with. There's a few more. I would like it to be robust to small failures. If something goes wrong, if some like disk read goes wrong, I'd like it to gracefully just try that again. If something more serious goes wrong, I'd like to be able to checkpoint, save my progress, make a video game, come back to it later. And finally, I'd like it to be fully open in all senses. So I don't particularly want, like, even if this mythical software existed, but everybody had to pay like one vendor in order to use it, that wouldn't be great from the point of view of open science. I'd want to at least have the ability to move to a different vendor or understand the software well enough that if it got commercially licensed or something, I could recreate it. So with those in mind, I'm going to start explaining what cubed is. So the basic idea of the cubed package is that all array, you imagine taking all array operations from one Zarr store to another Zarr store. So start off with some Zarr store in a bucket somewhere, apply some array operation to the chunks, and you end up with another Zarr store. And you think of all workloads that you want to do as such a succession of operations on Zarr stores. Notice that this is kind of similar to what happens if you are struggling to use a parallel framework. Like if you have problems with Dask, a common anti-pattern kind of is to get halfway through the computation, save your results out to Zarr, and then try the second half of the computation. So in some ways, this is kind of similar to just formalizing that sort of reliable pattern. The next insight is that of array analysis operations that we want to perform, many of them can be described as blockwise. So a simple example would be an element-wise addition operation. It's blockwise in the sense that it's like multiple inputs here become a single chunk in the output. You can imagine a generalized version that's like an outer product, but you only for this to understand this, you only really need to think of a simple example like an element-wise addition. So the point here is that one task can take a single chunk from the two different arrays that you're adding and write out that single result to the second Zarr store, the output Zarr store in that operation step. That covers a large class of operations already, but obviously not all of them. Some of the trickier ones require a rechunking step, and this is normally where stuff goes wrong. In other distributed systems contexts, this is sometimes referred to as like a shuffle. But we can do this between Zarr stores as well. And in the Rechunker package, then in the Pangeo community, we made an entire package just to deal with the problem of changing the shape of chunks from one Zarr store to another Zarr store. And Ryan and Tom Augsburger came up with a clever algorithm that basically can guarantee that you can always complete this in a fixed amount of memory so long as you use another intermediate Zarr store in the middle. And that's okay for us in cubed. It just means that we have an extra Zarr store inserted in this operation. That covers another class of operations, but some operations require both blockwise and rechunk together. An important example would be a reduction. It turns out that you can express this as a blockwise operation followed by a rechunk, followed by a blockwise, and you repeat that loop as many times as you need to create the tree to get from a large array down to, say, a small aggregated result. But it turns out that that's actually all you need. You only need blockwise and rechunk, and you can cover the entire space of numpy-like array operations. And this is the clever insight that Tom White came up with. So we can, here's a representative example, a representative selection of NumPy array API functions. So we've got addition that we talked about, and reduction would go in here as well. Well, reduction would be a primitive, but a sum would be an example of a reduction. And the point here is that you have this top level API, you have these intermediate core operations, but ultimately everything is expressible as just some combination of blockwise and rechunk. And if you want to do an entire workload, you obviously need to do more than just one array API operation. So you chain the operations into a high level plan, which is essentially a DAG. And we can do this at an array level rather than a chunk level now. So if we did, because we're only talking here about processing arrays, we're not talking about processing totally arbitrary computations, then our addition operation might be represented as the array that goes in A, the array that goes in B, the result. You can see here the BW stands for blockwise because this is a blockwise operation. And in this case, there are 4 tasks underneath here. Maybe there's 4 chunks in here, but this could be 1,000 chunks, and this graph would look exactly the same. That's the number of chunks is just abstracted away. And like the cluster, the number of chunks is like an implementation detail that's kind of irrelevant to the practicing scientist. The blockwise and rechunk operations both have an extremely nice feature, which is that the blockwise operation only processes 1 chunk at a time, and the rechunk operation can be constant memory using the algorithm from the Rechunker package. Which means that both of them have this property of, you only need to process 1 chunk at a time, and you know how large that chunk is, which means you can constrain how much memory usage you expect to have to use to do that process. And because we can express everything in terms of the blockwise and the rechunk operations, that means we can express our entire workflows in terms of things that we can predict the RAM usage of. So that means that before we even start running the computation, so once we've built the graph, but before we've actually started executing anything, we can see whether or not we're going to have enough RAM to process chunks of the size that we specified, which is huge. You can imagine this as you project how much memory you're expecting to use based on the type of operations. So for example, if you were adding 2 arrays, you would need twice the RAM of each chunk because you've got to hold them both in memory to add them together, maybe. And then when you actually run it, you'll get some variation below that, depending on the exact internal details of how NumPy executes its loops, but you can put an upper bound. And then, so all you have to do is say at the start, okay, we have an allowed amount of memory that's greater than the amount we expect to use. And as long as we've got some headroom here, we should be pretty confident that we can complete this. So we've got this picture now of Zarr to Zarr operations acting on many chunks. Each chunk can be executed basically separately. Each task can process 1 chunk separately, which has nice memory properties, but it also lends itself to serverless execution. So if every operation between, so Zarr store to Zarr store, one operation like that is a set of potentially very many embarrassingly parallel tasks. You imagine adding just number 1 to every element of a massive array. If that array has 1,000 chunks, then it's just 1,000 embarrassingly parallel operations that you want to perform at the same time. So we could just, in an ideal world, we just launch them all simultaneously, which is actually an ideal fit for so-called serverless cloud services, where instead of spinning up a cluster of a specific size that then works through all of your tasks sequentially, instead you abstract away the small unit of computation you want to do as a serverless function. And then you just ask some like cloud-based service to execute the number of those that you actually want to do. So in our case, we would say, okay, we need 1,000 little jobs done, and each little job has to process 1 chunk. So let's go to a service like AWS Lambda and just ask for 1,000 of those jobs to start going. And this is what serverless means in a modern context. And it's something that you can basically get off the shelf from cloud providers. So for example, AWS Lambda, but also Google Cloud Functions, every cloud provider has a version of this. And this means there isn't a cluster because we start with a Zarr store, we specify the embarrassingly parallel tasks we need to run, we ask the service to do that, it launches them all, worries about it for us, they write out, they're immediately ended when they finish their write out. And at no point did we have to like create a cluster of a specific size or just turn it on or shut it down. So I mentioned that there are various different serverless cloud services. Cubed actually generalizes slightly further than that to a range of different executors. So Cubed has this high-level abstraction of the workload that you want to perform in terms of moving from Xarray to Xarray. And we can abstract the execution of this DAG over different cloud vendors. And a particularly useful library for doing this that Cubed uses internally is called Lithops. And what Lithops does is allow you to abstract over a range of different cloud vendors. So Lithops allows you to basically dispatch your embarrassingly parallel tasks and hand them off to AWS Lambda or to Google Cloud Functions or whatever. And Lithops just worries about that layer for you. But that's already great. But that's not the only way that you can run Cube, because you can also imagine creating other executors to execute your DAG, because the DAG is quite as a series of set of embarrassingly parallel tasks, and any parallel framework worth its salt should be able to execute this. So another interesting example is this startup called Modal that's basically very fast spinning up cloud containers and can give you things like access to GPUs. Another interesting option is to actually run it with Dask via coiled. So you end up using Cube to create the plan and then eventually end up turning it into a Dask graph to run on coiled functions, which is this sort of pseudo serverless offering from coiled. And that's kind of interesting because the end result is almost as if you had rewritten Dask array to use Cube's abstractions for the blockwise and rechunk operations and the bounded memory properties rather than the heuristics that Dask array normally uses. Another option is Cubed allows you to serialize your DAG to a Beam pipeline and then execute it on Google Cloud Dataflow, which is nice because that's quite a mature technology that's used to process large amounts of data. So there's another cloud service for processing large amounts of data. So that's a lot of different components. So how do these all fit together? So the overall design, hopefully now you understand why the title talked about bounded memory, because we can constrain the memory in advance, why it's serverless, and how we're processing just arrays. So the overall design ends up looking like this, where at the top level, what the user sees is an array object like a NumPy array that has the various functions that you would actually use, or that a high-level library like Xarray would actually call. So that's the NumPy-like API. Then those are implemented in terms of these core and primitive operations like map blocks, reduction, apply ufunc would be in here, blockwise and rechunk. And these are abstractions that are implemented within Cubed, but were really invented or coined by Dask. And they just turn out to be very useful ways to express parallel array computations. Then the runtime layer, you can run it on Lithops, Modal, you can run it in process for debugging with Python. And a lot of the power comes from the Lithops library here. And then at the bottom, we have a storage layer, which is conventionally Zarr. So we've done some testing of Cubed, and in particular, I wrote a blog post where we tested Cubed on the so-called quadratic means problem, which is basically a simple to express problem from the Pangeo world, but it sometimes causes problems for other parallel frameworks in terms of managing memory usage. You can look in more detail in the blog post, but it shows that we can quickly scale up to 1,000 containers. And you can see that in this graph. So on the vertical axis, we've got number of functions being called. And here there's like, in fact, there's like 4,000 containers immediately being spun up here. And they all get spun up into the vertical blue line means they all get spun up simultaneously. There's some of them take slightly longer to finish than others, and they are ordered by how long they took. But after this is complete, that's like one Zarr store to another Zarr store. And then the whole workload gets expressed as a series of such steps, each of which scales up in a really nice horizontal fashion. We can also show that during this computation, the memory usage was controlled. So you can see this graph basically shows the allowed overall memory usage per container in gigabytes. So in this case, we're spinning up a series of containers, each of which had 2 gigabytes of RAM. And you can see that we sort of set this upper limit. You can project the maximum that you think is going to actually be needed at each point in the computation. And as long as that projected doesn't exceed the allowed, then you're permitted to proceed with the computation. And then the blue is the actual usage tracked over time as it ran. And you can see that it was well below the threshold and the computation was successfully completed. Overall, the blog post shows how, at least at the moment, cubed was slower than Dask and coiled run on the same problem, which is not hugely surprising given the amount of I/O that we're doing. But there's plenty of room to optimize some of these results through, for example, we could be a lot more aggressive with stuff like task fusion. But I encourage you to have a look at the blog post. So this seems nice. Wouldn't it be cool if Xarray users could just try it out and not have to worry about the details of how all this works if it was just abstracted away from them? So this part was really my contribution. The writing of cubed was Tom White. So as an Xarray dev, I generalized Xarray so that you can... Oh, wait, hang on, I've got slides slightly in the wrong order here. Xarray has been generalized to wrap any chunked array type. So all you have to do is install cubed and install this little glue package cubed Xarray. And then before you use cubed, you need to specify the allowed memory. So you have this spec object in cubed where you basically just say, I'm only going to allow 1 gigabyte of memory per container. And I want the intermediate results to be written. Here would be a local directory, but in general, it's supposed to be a cloud bucket. And then once you've done that, then you can pass the spec object to Xarray Open Dataset by saying chunked array type is cubed rather than the implicit default, which is now Dask. You immediately get to open your Zarr or netcdf or whatever as a chunked cubed array, where you can see it refers to a plan and the number of chunks in the plan, obviously taking inspiration from the Dask array repr. But the point is that all you have to do is add these extra keyword arguments at the start of your Xarray analysis notebook, and now you're ready to run with cubed. So at the end, you just compute, same as you would with Dask. So in order to compute, you have to choose the executor you want to run on. So for example, if you want to run with Lithops, you have to import the Lithops executor from cubed, and then you just pass that to the compute call, the Xarray compute call. You need to configure the permissions in the bucket underneath first, but that's really it. Like you only really need like these extra arguments to your existing Xarray functions in your notebook to actually try this out. So now that Xarray wraps cubed or Dask or potentially other things because of the way it was generalized, then how should we think about this new power? So in the tabular data world, we have this language, this query language called SQL, and SQL allows you to gives you a high-level way to express various different types of computations you want to perform on tabular data. But the expression, the SQL code itself, can be executed in many different ways on many different technologies. So some currently fashionable ones are like DuckDB and Polars, but there's also like SQLite, and there's a whole zoo of possible backends to execute your SQL queries with. So can we make an analogy for this for array data? So in the array data world, Xarray works quite well as analogous to SQL in the sense that when I do dataset.mean dim equals time, it's a high-level abstracted way of expressing the analysis query that I want to do on my multidimensional data. And previously, your options for executing that query were NumPy or Dask, but now it's been generalized. You could also execute it via cubed, or there are other nascent technologies that could be used here as well. And what I'd really like to see is, in the same way that there's a zoo of competing backends with different properties and different use cases in the tabular data world, I'd like to see a zoo of different array backends competing. So Dask, cubed, CuPy for GPU arrays. I want to see other options as well. And I'd like us to be able to switch between them as easily as you can take a SQL query and run it on different backends. So if we go back to my Christmas list at the start, we can see how close we get. So is cubed expressive? Yes, it's just as you can't do non-array computations, but you can do any of the array computations that you need because you can the same abstractions of map blocks and reduction, apply ufunc, and so on are present. Does it scale well horizontally? It doesn't scale perfectly, but it's designed from the start to scale pretty well. And if you're doing something like an element-wise operation and that was all you're doing, it would be basically perfect horizontal scaling. That's kind of the whole point of the serverless design. The serverless design also means there's no cluster to worry about. So you can't accidentally get charged for leaving a cluster running or something like that, not using it. You're only paying for the computation you do. That's another feature of the serverless model. Does it have no nasty surprises, predictable usage? Yes, because of the bounded memory thing that at least removes like a very significant class of possible problems. Cubed has some other nice little hidden features like retrying failures of individual tasks, and resuming from a workload that you stopped halfway through. And is it open? Yeah, it's open source, and it's not actually like intrinsically that complicated. Like there aren't magic numbers underneath that you would, if you wanted to rewrite cube from scratch, then you would obviously have to be pretty good at programming, but you wouldn't have, there aren't like magic numbers that you'd have to find out by trial and error. Like all the information is here. So what are the downsides of it? So reading and writing from Zarr is going to be slow compared to, if you could do the computation without moving stuff to and from disk storage, then obviously that will be faster. So this alone indicates that what you might want to do is think of cubed as like a backup option. So if you try to run Dask on something and it doesn't work, then try out cubed, and it might take a bit longer, maybe, depending on the structure of your problem. But the idea is that it's more predictable. And then per CPU hour, serverless is currently more expensive, but the direct cost trade-off is a little bit more complicated because you're paying more per CPU second, but you are avoiding costs by having a cluster idle that you weren't using. So you're only paying for the CPU hours that you actually used. And another disadvantage is that cubed can only do array operations by design. So we can't do this on a data frame. We can't do some weird custom computation on like a social network or something like that. So what are the next steps? So we'd really like to have more use cases to test this out on. We have a repository that I'll link to for collecting such use cases. And in general, the community really benefits when people bring up things that they thought were going to run, but actually don't run very well. Pangeo's like made quite a lot of progress by basically just like identifying common pathological use cases and improving their performance in various ways, both in Dask, in extensions to Dask like Deepak's Flocks package for group buys, But we'd like to do the same thing with Cube because it has different structure, so it needs to be tested in different ways. There are a lot more optimizations that could be done within Cubed in terms of task fusion. And in this context, if you fuse two tasks, it means avoiding writing to a Zarr store. So you gain a lot by doing that. The tricky bit of the optimizations are writing optimizations that don't lose the nice properties of bounded memory. It would be great to generalize Cubed to wrap other array types. Like it would be very cool to be able to wrap something like JAX or like CuPy arrays or something, and that might unlock some interesting new use cases. Similarly, with other storage layers, anything that improves the I/O speed is a big improvement to the speed of Cubed. And so Google TensorStore is one interesting option there. And then also, Cubed is obviously quite closely tied to the capabilities of Zarr. And so any improvements to Zarr benefit Cubed, basically. And there are various features there that are in progress or being discussed, which would be quite exciting. So overall, if this is interest to you, go and read the blog post, join the discussion. We have been running this working group for distributed array computing that anyone is welcome to. We've been focusing on Cubed recently, but any other parallel array frameworks that could conceivably be run with Xarray are also of interest. Thanks to Tom, who's in the audience. And yeah, that's the end of the presentation. Thank you for listening.